problems 35 and 37, we have a similar situation, except we're starting with a graph. We're given the function, for example, in 35, y equals x minus x squared. We're shown the graph of that function, and we're asked to find the area. In order to find the area, first we have to set up a definite integral. So for number 35, we would have the integral x minus x squared dx, and you can see that the limits of integration here will be from 0 to 1. And so that's all you need to do to set that up. We'll find the antiderivative of x. That becomes x to the second over 2. The antiderivative of x squared is x to the third over 3. And again, that's from 0 to 1. And fortunately, when we plug in 0, everything is going to 0 out. When we plug in 1, we're simply going to get 1/2 minus 1/3. And that's 3/6 minus 2/6, or an area of 1/6. Alright, for number 37, similar situation. We have an integral of cosine of x. We're looking for the area between the cosine curve and the x-axis, and between the x values of 0 and pi over 2. So the antiderivative of cosine, simply sine. So we're going to evaluate the sine curve at pi over 2, and that's 1. The sine curve at 0 is 0, and we end up with an area of 1 in that case. So with a problem like this, you're basically looking at the shaded region that's given in the graph. You're given a function, and you have to determine the limits of integration, set up the integral, evaluate the integral, and find the area. Alright, I'm going to scroll down and go on to the next group of problems. Okay, from 39 through 44, we're given the boundary equations of an area, and we need to set up the integral, determine the limits of integration, evaluate the integral, and find the area. So the first one is 5x squared plus 2, x equals 0, x equals 2, and y equals 0. So if you think function transformations here, we're starting with the x squared function. We're going to multiply that by 5, which is going to make it steeper, and then we're going to shift it up by 2. So essentially, we have something that looks sort of like that. And we want to find the area that is bounded by the curve y equals 5x squared plus 2, x equals 0, which is the y-axis, y equals 0, which is the x-axis, and x equals 2. So that's an area that is going to look something like that. And so our integral will be the integral from x equals 0 to x equals 2 of 5x squared plus 2 dx. So we find the antiderivative. Antiderivative will be 5x to the third over 3, or 5/3 x to the third plus 2x. From 0 to 2, again, when we plug in 0 here, we're going to get 0. We won't always get 0, but in this case, again, we do. So we need 2 to the third, which is 8, times 5/3. So 8 times 5 is 40 over 3 plus 4. And if we write the 4 in terms of thirds, that's 12/3, and we should end up with 52/3 there. In this case, we'll bring in the calculator. I think on all these it's helpful to visualize what the area is, or what the region is that we're looking to determine the area for. And so we start with our function 5x squared plus 2. The window on this, I'm going to let my x values go from -3 to +3. The y values, we are going to need a little bit higher than 10, I believe. So I'm going to go from -10 up to +50 by 5s. And when I graph that, I'm going to get something that looks like that. And I want the area from 0 to 2. And you can see that that's 17 1/3. 17 times 3 would be 51, and 1/3 would give us 52/3. So again, if I store that value in alpha A, and just so that I can see what it is there, and I compare that to 52 divided by 3, you'll see that we get exactly the same answer there. Alright, so that's number 39. We'll go on to number 41. 41, we have 1 plus the cube root of x from x equals 0, x equals 8, and y equals 0. So I'll bring the calculator back and we'll take a look at what it looks like here. So we have 1 plus cube root of x is x to the 1/3 power. And we're looking for, again, y equals 0 is the x-axis, x equals 0 is the y-axis, and x equals 8. So in our window, we at least need to show, let's go from -1 up to +10 by 1s, and say -5, I think, to +5 should be sufficient by 1s. We'll take a look at that graph and see what we get. Okay, and we're looking for this between the curve, the x-axis, which is y equals 0, the y-axis, which is x equals 0. So we want all of that area from 0, x equals 0 to x equals 8. And option number 7, 0 to 8. And we'll see. The calculator gives us 20, the 0.000038. We don't need to worry about that. That's just calculator rounding error there. So the answer should be 20 here. So let's move the calculator out of the way and come back and do our integral. So we want the integral from 0 to 8 of 1 plus x to the 1/3 power dx. Alright, so the antiderivative of 1 is x. The antiderivative of x to the 1/3 is x to the 4/3 divided by 4/3, same as multiplying by 3/4, and from 0 to 8. So first we're going to plug in x equals 8 plus 3/4 times 8 to the 4/3 power. Again, a simple way to do this, and finally when we plug in 0, we're going to get 0 for all of the second part of this. The easiest way to find 8 to the 4/3 is to remember that a rational exponent is power over root. So we have the 4th power and the 3rd root. We can either take the power first and then find the root, or take the root first and then find the power. So we'll take the 3rd root, cube root of 8 first, which is 2. 2 to the 4th power, which is 16. So we get 8 plus 3/4 of 16. and 3/4 of 16 is 12. 8 plus 12, and that gives us the 20 that we were looking for before. Alright, we'll go on and do number 43, and then we'll close out this video. So here, I'll bring in the calculator. So we have our function negative x squared plus 4x, and the only other boundary that we're looking for is y is equal to 0. And so it's hard to tell exactly what we're going to need. Let's start off with a standard window here. And you can see that the parabola makes the little arch in the first quadrant. So all we're looking for is the area between the curve and the x-axis, or y equals 0. So in this case, I believe that that's going to be when x is equal to 0. And we have to determine the other one. Now we could determine this algebraically, or we can do it using the calculator. Let's see with the calculator. I think they're going to be pretty straightforward answers here. So we want second trace. This time we're going to use the 0 option. We're looking for the zeros of the function. We have to go a little bit to the left, hit enter. That is, we want to find the place where this graph crosses the x-axis. A little bit to the right, guess, you just hit enter, and we see that that's at 0, 0. Then there's another one, so we're going to go second calc, find another 0. This time we have to move closer. The calculator will find the closest 0 to where you are. Our left bound is going to be just above where it crosses the x-axis, right bound just below, guess is enter, and so it's x equals 4. So we use the calculator to do that. I'll show you how to do that using algebra, and we'll move the calculator out of the way. So if we were to take our function negative x squared plus 4x, and we want to find out where it crosses the x-axis, that is where y is equal to 0, and we would get something like this. We can factor out an x, and we would get negative x plus 4 equals 0. And we can see clearly that that's at x equals 0 and x equals 4. So we're going to let those be our limits of integration. 0 to 4, negative x squared plus 4x dx. Antiderivative of negative x squared is negative x to the third over 3. The antiderivative of 4x is 4x to the second over 2, or 2x squared. And I'm going to evaluate that at 4. So 4 to the third power, 4 times 4 is 16, times 4 is 34. I'm sorry, 64. Negative 64 over 3. Then 4 squared is 16 times 2 is plus 32. And we're going to end up with, we have negative 64 over 3, converting the 32 to 96 over 3 gives us a positive 32 over 3 for the answer there. And I think since we have everything set up on the calculator already, we can go back to our graph, take the integral from 0 to 4, and you see that that gives you 10 2/3. 10 2/3, 10 would be 30/3, and 2/3 would be 32/3. So we're all set there. All right, that's going to do it for these for this section of problems, and we'll continue in the next video.